All right, so we got this sort of thought experiment. I got a spring hanging from the ceiling, and it starts off at an undistorted length, x naught, and we're going to slowly add more and more mass to this thing. And I think just to define that x naught height, I'm going to send a dotted line across the page. By the way, if you're somebody who wants to play around with this, there are some great apps for this one, for just playing with it virtually, or you can just take a spring and hang masses off of it. But if you hang masses off it, in fact, we may do a lab in the future where you have to do exactly this and do kind of the process that we're doing right now. And so in a way, I think we were doing a little bit of a pre-lab here, where we might talk exactly about how to do the lab analysis for figuring out the elastic coefficient. Oh, there's the word that got away from me, for this spring, okay? So we've got a mass that's hanging off of this thing. I'm going to call it FG1, because I would call this mass 1. And we could say that mass 1 is 1 kilograms. And we could say, okay, well, let's make mass 2 be 2 kilograms. And let's make mass 3 be 3 kilograms. And I'm not too worried about significant figures here. I just want to talk it out as a conversation. And I'm not even drawing free body diagrams. These are just force illustrations. And I can say, okay, well then, for this first one, I would have delta x1. And there would be, if it just hangs at a steady height, equilibrium position, there would be Fs1, spring force 1, that's keeping that mass upwards. And then for the next situation, I'd have Fg2 for mass 2, and of course spring force keeping it upwards, Fs2. And associated with that, there would be a delta x. Now, really, here I am kind of being a little bit laissez-faire about where I'm measuring my delta x from. If I'm measuring from the bottom of the spring, then I got to measure consistently from the bottom of the spring for my delta x value. Notice that the mass is changing size, so I have to be consistent about where I'm measuring my delta x values from. Really, it's the bottom of the spring position in the first position to the bottom of the spring in each successive position. So delta x2, mass 3 is going to give us, here I am being better about my consistency, delta x3. And there's going to be an Fg3 and an associated Fs3. And what we get for this is and honestly, you can even see it visually. Of course, I was intentional about how I set it up, but if you use a real spring or a series of even identical springs, as identical as you can, and you just connect the dots through these values, can you see that this is going to be a linear relationship? There seems to be a linear relationship, at least for my cartoon of this situation. And Hooke saw that there really was a linear relationship with real springs, so long as you didn't stretch them too much. That's what's ideal about this situation. You want to have metal that behaves this way. So long as you don't stretch it beyond its limit to behave this way, it's going to be considered to be ideal. So I take my data and I recognize that Fg is equal in magnitude to Fs for equilibrium. So I could have a table 1. And of course I would come up with a descriptive title. And I have friends in different science discipline areas telling me that I got people in this grade level that are still not formally titling their tables and graphs. And they're asking me, are you telling them to? And I'm like, yes, I absolutely am telling them to. So we got to make sure that we have numbered tables. We want to make sure that we have headers with units, appropriate variables. Now, I'm doing this somewhat informally. I'm not having any words in my headers. So we might say spring force, and then, spring force, and then comma Fs for the variable. That might be something that's asked of you by a teacher. But we'd have our table, and we would record all the different values that would be associated with all the different delta x values. So we're measuring forces, or calculating forces, based on our Fg values. And then we could graph this thing. Say, let's take this data. Like I said, in some ways this is a little bit of a pre-lab for an activity that we may do in the not too distant future. Fs in newtons, delta x in meters. And I don't want to put any numbers on this because I haven't yet. What Hooke did was he made these measurements and it turned out to be linear. As the force increased, the amount of stretch increased. And of course, when you have data that's linear, what do? You add in a line of best fit. Nice thing about this is that it went straight through the origin. Boom, great. And you know, while we're on the topic of being formal, this is another thing that I've been hearing about, is we want to make sure that we have our titles. I'm just going to call this figure 2. The reason I'm calling it figure 2 is the picture of the spring up at the top of my page was called figure 1. So figure 2, in our same subsection, is going to be spring force in units of newtons versus spring distortion. And ideally, we wouldn't wrap a title around 2 lines like this, but I have a layout issue. In meters. Underline your titles. There may be people that want to see the word spring force and then comma FS brackets newtons in the vertical column too, or vertical axis as well, okay? So be aware of what the requirements are for your instructor or whatever the marking scheme is. I want to make sure that I'm consistent with all the other areas of science. We're all giving common messaging, so you're not relearning like the physics way versus the chemistry way versus the biology way, okay? We want to say that this is the way. Very Mandalorian of us. All right, so the weird thing about this is that you don't always have an ideal spring, and you might end up having a graph that looks like this. Might end up being delta x, Fs versus delta x that ends up being, this is not ideal. This is not an ideal Hooke's law spring. What we would be saying here is that this spring seems to require more force to get the first little bit of stretch, then not very much force to get the next bit of stretch, like a lot of stretch actually, and then a lot of force to finish the job. And I can't think of what that spring might be. Maybe there's rubber bands out there that are like that, you know, like it takes a little bit to get them going. I actually wonder if maybe there's something in some kind of bungee cord where you can imagine like it doesn't take a lot to get it, or it takes a lot to get it stretching at first, but then once you start falling and really pulling on it, maybe it really lets you fall a long ways, and near the end it kind of snaps you, just to give you a little thrill at the end. That could be a thing, but you know, I would have to do some research on that sort of stuff. But what we would say in general though is this is a non-ideal spring. If we had a relationship like this. And you could even check that, see that there's inflection points and it's not linear. Whereas this guy here would be an ideal spring. And so when we're talking about Newton's ideal, not Newton, we're talking about Hooke's law ideal springs. We're talking about relationships like this, okay?